Let's look at some exercises now that are working with inequalities. So I encourage you to try these on your own. And if you're stuck, just remember most of these will be a lot easier if you use the 4 axioms we discussed. So let's look at the first one. So if x is any real number, prove x squared is greater than or equal to 0. There are many ways to approach this, and we want to be rigorous, so obviously we know this is true, right? If we have a graph of y equals x squared, right, it's a parabola, and it's above the y-axis, except at the point 0, right? It's at the origin. So this should be, right, this is true, but how do we show this? And we're not going to use a graph. That's not rigorous. So let's write our proof here. Okay, so all we know is that x is a real number. So we know that x is a real number. And we need to prove that x squared is greater than or equal to 0. Okay, so there are a few cases. If x is a real number, x is either a negative number, x is either a positive number, or x is 0. So we should look at these 3 cases, right? We discussed the mutually exclusive stuff in the, I believe it was the second lecture or third lecture about inequalities. So we're going to use that idea here. And you could do the greater than or equal to stuff like we discussed as well. We don't have to make it mutually exclusive, but I'm going to show every case individually. So I'm going to get rid of this x as a real number. We don't really need that. So let's say, let's start with the case where x is a positive real number. So case 1, x is a positive real number. Okay, well, and I'll be a little bit more rigorous. I'll say let x be a positive real number. Now, recall by our axioms, we want an x squared, right? So I think it would be smart to just multiply both sides by x. And can we do that? Yeah, we can. Remember axiom 3, we're assuming that x is positive. So we can multiply both sides by this positive value, and the sign won't, or the inequality sign won't flip. So we can multiply by x, and we get, so we have x is bigger than 0, and then we can just multiply both sides by our x, and we get x squared is greater than 0. Cool. So we've shown for the case for positive real numbers. Now we need to show it for, we'll do it for negative numbers. So this time we'll let x be negative. So let x be a negative number. Same idea here. We can still multiply by x, but we need to make sure we can multiply by x. But we need to make sure x is a negative real number. It's less than 0. So we're actually going to have to use, this will be up here, I'll label them. So the one we used up here was axiom 3. We're going to have to use axiom 4 for this problem since x is negative. We have to flip the inequality sign if we multiply both sides by x. So we have the assumption that x is less than 0. And we can multiply through by x. That's totally fine. But since x is less than 0, we're going to have to get x times x is x squared. We're going to have to flip the sign, so it's going to be greater than 0. So for positive numbers and negative numbers, we get x squared is greater than 0 and x squared is greater than 0. Perfect. But we're missing one thing. What if x is 0, right? Because 0 doesn't fall into both of these cases. And one could argue you could do this with, right, a less than or equal to right here, and then just do that, and then you'd be done. But I'm just going to show all three individually. It'll be good practice. So I'll just put it over here. So we'll say let x be 0. Again, we'll multiply by x, so we have x equals 0. We will multiply through on both sides by x. And we will get x squared equals 0. So our three cases have resulted in x squared is greater than 0, and x squared is greater than 0, and x squared is equal to 0. With this information, we can say thus x squared is greater than or equal to 0. Because of that last case, we have that equal to. If we didn't have that last case, it would just be greater than 0. But since that last case equaled 0, we need that equal to 0. So if x is any real number, if we square it, it will be 0 or positive. And that's it. Put a little box here for that. Let's look at the second part of this. So if a is between 0 and 1, that's what that means. That's what this weird looking inequality says. So if a is between 0 and 1, not including 0 and 1, and b is greater than 1, we need to prove these two statements. So we'll prove the first one first. So we'll say proof of 1. What I'm looking at here, we need an a squared from this a up here, so I'm probably going to have to multiply by a somewhere. And same thing here, I'm going to need a b squared, so I'm probably going to multiply a b over here. And I also see that they give us this, or we need to prove that a is less than 1, and we also need to prove that b is less than or greater than 1. But if you see, like, if you really pay attention, they give us that information already right here. We know that a is less than 1, and we know that b is greater than 1. So really, all we have to do is prove that 0 is less than a squared, and b squared is greater than b. That's what we really have to prove. So let's do that. So we'll just look at the first case. So we assume a is between 0 and 1. And by our axiom, I'm going to multiply everything by a. Now, is a positive or is a negative? So do I use axiom 3 or do I use axiom 4? Well, in this case, a is between 0 and 1, which means it's strictly positive. So we will use axiom 3. So we'll say by axiom 3, we multiply by a. So we have, this is what we have, this is our assumption right here. And I'm going to multiply each term by a, multiply that by a, multiply that by a, multiply this by a. A times 0 is 0. A times a is a squared. And 1 times a is a. So we're almost there, right? We want to prove that 0 is less than a squared, which is less than a, which is less than 1. But we only have like the first three. But remember what I said earlier, we already have the assumption that a is less than 1. So we can kind of just tack that on to the end. right? We already know this information. We know that a is less than 1. So this is what we want. We know that 0 is less than a squared, which is less than a, which is less than 1, assuming that a is between 0 and 1. And that's it. Put a period there. And we'll look at the second one. So I encourage you to try this one. It's a very similar technique as well. Okay, so we're going to assume the same thing. In this case, we're going to be assuming the b case, though, since we're using b now. So assume b is greater than 1. I want to prove b squared is greater than b, and b is greater than 1. Well, I see a b squared, so my idea is I'm going to multiply everything by a b to get that b squared. And again, it's either axiom 3 or axiom 4 we're working with multiplication. In this case, b is a positive number, so we're going to use axiom 3. So by axiom 3, we multiply through by b. And when we do that, so we have b is greater than 1, and we can multiply both sides by b, and we get b squared is greater than b. We don't have to change the inequality sign. And again, we're really close. We have b squared is greater than b. And again, we know that b is greater than 1 already. That's our assumption. So we can tack on that b is greater than 1 down here. And I just realized that I was a little too far. That's fine. So we multiply both sides by b, and we get b squared is greater than b. And we can just tack on the greater than 1, because by our assumption, b is greater than 1. So it's just like that last part. And that is also it for that proof. So that would be the first question. So 1.8, that is how we will prove those.